All right. So in our last class meeting, which was done online, we talked about electromechanical energy conversion and let's see where we wrapped up was here, where we were talking about the reluctance torque of a rotating machine. And then I believe I said we were going to kick things off this class meeting by talking about cylindrical machines. So let's go ahead and do that. Yep. My TA should be literally working on editing the video right now. So a cylindrical machine is a special type of rotating machine. And again, you're going to have to deal with my inability to draw a circle. So I'm going to go ahead and pre-apologize. So let's say that we have a situation like this. So this is supposed to represent our stator. And our stator will have an associated winding. So here is current flowing out of the page, and 180 degrees across is current flowing into the page. And then inside of, let me actually go ahead and write this out right here. And so this is going to be our stator axis. And then inside of our cylindrical stator, we are going to have a cylindrical rotor as well. So, and I'm going to choose to orient my rotor winding as a little bit askew from the stator winding so that we can define our rotor axis like so. And then this angle measured from the stator, which is stationary, to wherever the rotor currently is an angle theta that depends on the mechanical rotational speed, omega m, as well as time t, as well as this lowercase Greek letter delta, where delta is the rotor position at t is equal to 0. So think of it as effectively like a physical phase angle. So if the rotor and the stator are perfectly aligned at t is equal to 0, then that angle delta would be 0 degrees. But as the rotor is more askew from the stator, that angle gets larger and larger and larger. Okay. So in a system like this, the air gap is constant, which means we will not have any reluctance torque whatsoever because the self-inductance of our stator windings and the self-inductance of our rotor windings do not change. So the only thing we're going to have is that mutual inductance component. So our developed torque T should be the stator current as a function of time times the rotor current as a function of time times the derivative of the mutual inductance between the stator and the rotor as a function of our angle theta with respect to theta. And our mutual inductance will typically have a form m naught cosine of that angle theta. So our mutual inductance is going to effectively oscillate between a value of positive m naught when everything is perfectly aligned and negative m naught when our windings are 180 degrees out of phase, meaning that the dot here would line up with the cross down here, and the cross down here would line up with the dot there. So 180 degrees out of phase, we're going to have a negative mutual inductance. because the fluxes generated by both of those windings are going to oppose each other. When they're lined up perfectly, the fluxes generated by those windings are going to line up on top of each other and add, and that's when we get positive mutual inductance. So let's see what happens if we allow our stator current, IS, to have some magnitude. So ISM cosine omega ST and IR of T, our rotor current, will be IRM cosine omega RT. Let me label a couple of things here because we have lots of different omegas going on. So omega M is the speed of mechanical rotation. Omega S is the excitation frequency of the stator winding. And actually, let's just throw another phase angle on here. Call that alpha. And omega R is the excitation frequency of the rotor winding. So in a system like this, we effectively have three different things oscillating at potentially three different frequencies. So there's a lot of different things going on, right? We can excite our rotor and our stator at different frequencies because we have a coil and we can apply a voltage source that's just operating at different frequencies, each of them. And then omega M is just going to be the speed at which our rotor is physically turning, which is going to be dependent on the torque that we develop and all of that kind of good stuff. So under these conditions, our torque T is going to be equal to negative the magnitude of our stator current times the magnitude of our rotor current times the maximum value of the mutual inductance times cosine omega ST cosine omega RT plus alpha sine omega MT plus delta. And so if we multiply these three sinusoidal functions together, this is going to come out to be a terrifyingly long expression. I'm already aware of that. I'm not going to go through the derivation. We're just going to kind of look at it and see what shakes out. So we're going to have negative ISM IRM times M naught divided by 4. And then I'm going to have 4 large, ugly sinusoidal terms. So I'm just giving you a warning now. So we're going to have sine of omega M plus omega S plus omega R. That combination of frequencies times time plus our electrical phase angle alpha plus our physical phase angle delta. And then to that, we're going to add the sine of omega M minus omega S plus omega R minus alpha plus delta plus the sine of omega M minus omega S minus omega r times time minus alpha plus delta plus the sine of omega m minus omega s minus omega r times time plus alpha plus delta. And all four of those sine terms added together or multiplied by that constant term out in front. So we have this horrifyingly large expression for our torque, okay? Let me ask you guys a math-related question here. What's the average value of a sine function? You're thinking 0.707 would be the square root of 2 over 2, but it's not that. So if I were to graph a sine function, let's just do it over here. It's going to start at 0 and increase something like this, right? What's the average value of that function? 0. So the average value of the torque, even though we have this big giant expression, is actually going to be 0, except in very, very specific cases, okay? So those specific cases are when omega r is equal to 0, and our phase angle then by definition has to be 0, because if omega r is 0, that means that our rotor current is a DC current. And our stator speed and our mechanical speed are the same thing, okay? So if we apply a DC current to our rotor and we let our rotor physically spin at the same speed at which our stator is electrically excited, we have what's called a synchronous machine, because our mechanical speed and our stator speed are the same thing. So the rotor's physical movement is synchronized to the stator's field, okay? So under these conditions, our torque T will have the following relationship. ISM, so the magnitude of our stator current, times our DC rotor current, times the maximum value of our mutual inductance, divided by 2, times the sine of twice omega st plus delta plus the sine of delta. And so now we have a torque whose average value isn't 0, because the sine of delta term out on the right-hand side is just going to be a number. So even though the average value of the sinusoidal component is 0, there's another term that isn't sinusoidal that's happening. So we're going to have an average torque of negative ISM IR M naught over 2 times the sine of the rotor position. So that's the average value of the torque. All right, so in this system, our torque is sinusoidally changing, but it's got like a DC offset, okay? So something like this. So here's torque as a function of time. I'm going to put something right here. So this is our average torque. And then superimposed on top of that, we're going to have sinusoidal signal like so. Since our torque is constantly changing, what do you guys think is going to be happening to the motor? Yeah, significantly faster. It's going to shake, right? It's constantly having fits and starts of a large amount of torque and then a small amount of torque and then a large amount of torque and then a small amount of torque over and over and over again. It's going to shake like crazy. So a system like this is perfectly acceptable if we're dealing with a very small motor because we're effectively saying we don't care if it's inefficient. So this would be like a single phase synchronous motor. But if we wanted something to do large industrial work, we would probably use a three-phase system because in a three-phase system, the amount of power that's being supplied to our motor is effectively constant, which means our torque will also be effectively constant, which means we won't have all of this vibration and all that kind of stuff that a single phase machine would have. So we can see here that we are developing some amount of average torque, but dependent on the situation, this might not be good enough. And so we might have to increase the level of complexity and go from a single phase machine to a three-phase machine in order to smooth our torque out and our power relationships and all of that kind of stuff out as well. So our second case is when omega m, our mechanical speed, is equal to the difference between our stator excitation frequency and our rotor excitation frequency. Yes, sir. So in this case, the stator winding and the rotor winding are both carrying AC currents. So neither of those guys are zero, okay? And the mechanical speed is just the difference. So we say that this system is working at an asynchronous speed because none of our omegas are the same thing, okay? So this is how an induction motor works. Okay? And that's what we're going to talk about later today in much, much greater detail, all right? So in this single phase induction motor, our torque is going to be equal to negative ISM IRM times M naught over 4. And then we're going to have another big sinusoidal function, but it's not going to be as scary as last time. The sine of twice omega st plus alpha, that's a terrible looking alpha, plus delta, plus the sine of twice omega rt minus alpha plus delta, plus the sine of twice omega st minus twice omega rt minus alpha plus delta, and then finally plus the sine of just alpha plus delta. So the average value of all of these sinusoidal components that are varying in time are once again going to be zero, but we're still going to have some DC offset average amount of torque supplied. That is just the sine of the phase angle of our rotor plus however much our rotor has turned, like its rotor position. The average value of this torque is once again just effectively the DC component. So negative ISM IRM times M naught over 4 times the sine of alpha plus delta. So once again, we have a sinusoidally varying torque in a single phase system, which makes sense because we know that the instantaneous power delivered to the motor is pulsating, so the torque should be pulsating as well. And we can correct this by using a three-phase system. All right. So before we move on to a crappy little PowerPoint thing that I made, does anybody have questions about this stuff. So this is electromechanical energy conversion. We talked about linear conversion of electrical energy into mechanical energy. And then we went into effectively torque being developed when we have a rotating electromagnetic system. Everything that we talked about here, expressly, I taught it from we are converting electrical energy into mechanical energy, but it absolutely works in the exact opposite direction as well. We can convert mechanical energy into electrical energy, literally using the exact same relationships. If we force the rotor to turn, we'll induce currents in our windings and all of that kind of good stuff as well. So it goes both ways. All right. So I've got this little PowerPoint thing. There's no real math relationships here that we are not going to see again multiple times. So there's really not a whole heck of a lot of reason to take notes for this part. We'll get into the nitty-gritty of how things work in a minute. I just chose to make this PowerPoint presentation because of how much a pain it would be to try to draw what these things actually look like. Okay. So we are going to start our discussion of the various types of motors that we're going to deal with in this class with induction motors. So there are two major types of AC motors. There's the synchronous motors and induction motors. And we have kind of talked a little bit about what those differences are a moment ago. In a synchronous motor, the rotor spins at the exact same frequency as the stator's electrical excitation. And in an asynchronous or induction motor, the rotor spins at a slightly different frequency as the stator. So, oops, all right, made terrible notes about what was slide number 1. All right, so here's a picture of an induction motor. This is one of two different types of induction motors that we have, but because it's an electric machine, we have some stationary part, which is the stator, and some movable part, which is the rotor. Each of them has their own associated winding, so we're going to consider the stator to be the primary winding that's going to receive external power to produce some amount of magnetic flux. And then our rotor is our secondary winding, which is going to receive its power from the stator through mutual induction. So effectively what we have here is a transformer. We have a two-winding system where one of our windings is the input that we put power into, and the other winding is the output that receives power from the primary winding. The big difference here is that now our secondary can turn. That's literally the only difference between a transformer and an induction motor. They are the same thing, except the secondary gets to spin, okay? So three-phase induction motors, or excuse me, induction motors in general are used in lots of different applications. So for three-phase motors, they're used in a lot of industrial and commercial applications like lifts, cranes, crushers, very large HVAC units. So like a compressor on a large HVAC unit for a building of this size is probably a three-phase induction motor, whereas the induction motor that runs a compressor for your HVAC unit in your home is probably a single phase because it doesn't have to do nearly as much work. Okay? Single-phase induction motors are designed for domestic and low-power applications like pumps, compressors, and all of that kind of stuff. One of the biggest advantages of an induction motor is that because it's designed so simply, it is extremely durable. I don't know how much time you guys have spent in Nethkin Hall, but you'll be over there next quarter taking the lab for this class. And I think Ron can attest that some of our induction motors in that power lab are incredibly old, like World War II era motors that are still running because they're induction motors and they just kind of last forever. Induction motors are the motors that you use in hazardous environments because they are so mechanically robust. You really have to try to break these damn things, okay? They are less expensive. They're relatively maintenance-free. They operate at high efficiency. So when fully loaded, typically we're off talking about power factors greater than 80%. So nothing too terrifying there. And a very, very large advantage is that they're self-starting, meaning that they generate a torque even when they're spinning up to their final speed. Whereas we'll see in a synchronous motor, it's not developing any torque until we actually get it up to synchronous speed. Okay. The principal disadvantages is that it starts off with very low values of torque compared to the other types of motors, and it has very high inrush currents. So effectively, when an induction motor starts, the current that's flowing through the stator windings is about 6 to 7 times higher than its steady state current, right? So if you've got a motor that's designed to draw, let's say 50 amps RMS, you have to be prepared for 300 amps RMS for a few milliseconds while this thing comes up to speed. Because effectively with the rotor being stationary, it just looks like a short circuit. So you have this short circuit current that you're dumping, or the short circuit that you're dumping a whole lot of energy into. And as it gradually spins up, the impedance of the motor gets larger and larger and larger until it hits steady state conditions, and then you're back down to the rated current and all of that kind of stuff. Another big disadvantage of induction motors is that speed control is difficult because they are designed to work at slightly less than a synchronous speed. So effectively, the speed at which an induction motor rotates is going to be tied to the electrical excitation frequency of the stator, which means here in the United States, induction motors operate at integer multiples of 3,600 RPM because 60 hertz translates to 3,600 revolutions per minute. And so we're going to get 3,600 RPM or 7,200 RPM or something like that for our speed. And the only way to really change that is to use something called a variable frequency drive, which effectively takes your signal that's at 60 hertz, converts it to DC, and then converts it into a signal at some frequency that isn't 60 hertz. So that's how speed control of an induction motor works. It's a bit of a pain in the butt if you need a speed other than something that's just a multiple of 3,600 RPM. All right, so let's talk about how things are made, okay? So much like when we were talking about transformers, our stator is made of very thin laminated sheets that are stacked together, and then we wind our winding around this stack of thin laminated sheets in order to make our stator. They are wound for a specific number of poles, which is determined by the speed requirement of the application. So we can add more poles to get different speeds, but it's still always going to be related back to that 3,600 RPM thing. So we can add more poles and all this kind of stuff to get different ones, but it's always going to be something related to 3,600 RPM. The synchronous speed is given here, NS, so that is 120 times the excitation frequency of the stator divided by the number of poles. So, okay. Then we get over here to our rotor, and we have two different types of rotors that we can see. Squirrel cage rotors on the left and wound or slip ring rotors on the right. The overwhelming majority of induction motors utilize a squirrel cage rotor because they're very, very easy to manufacture. So roughly 90% of induction motors are squirrel cage motors. They're very, very durable. The ones that we have over in Nethkin Hall that have been around forever are squirrel cage induction motors. The squirrel cage consists of effectively metal bars, so usually either copper or aluminum, and they're not quite parallel with each other. And we'll find out why they're not quite parallel here in a few minutes. So you get this weird kind of slightly askew spinning cage that's filled in with just material that holds it all together. And then for the wound rotor, or actually, let me go to the next slide here so we can see. So the picture's kind of grainy, but this squirrel cage motor doesn't have all of the discs and all of that kind of stuff, so that you can see how the bars are kind of slightly askew and all that kind of stuff. And that skewness is going to help effectively make sure that there's always a slight difference in the magnetic field, which is going to cause the torque that's going to make this guy turn. Like I said earlier, it consists of aluminum and copper bars welded together with end rings, and the bars are oriented slightly out of parallel. And there's pictures of the different types of slices that you can make these out depending on the number of bars that you need. And then lastly, we have here our wound rotors. Similar thing, made out of thin laminations with notches for the windings. The rotor will have as many poles as the stator, and it is always wound for three-phase, even if the stator is a single-phase stator. So the rotor is always three-phase in a wound rotor system. Slip rings are connected into a three-phase Y rheostat. So this is just a variable resistance so that we can get a larger starting torque out of this. So we have control over the resistance when it's spinning up versus just letting the impedance be whatever it needs to be. And so this helps us develop a larger starting torque. After it starts, then we short the slip rings out, and it effectively behaves in the exact same way as a squirrel cage rotor. All right. Thus ends my, like I said, very brief and crappy presentation on what induction motors look like. And so now, let's talk about how they work. Let me just delete all the stuff from circuits 1 and I'll use this here. All right. So we are going to be talking about three-phase induction motors for the duration of this. And we're going to go through things kind of step by step to figure out what's going on, okay? So the first thing that I want to talk about is the development of a rotating magnetic field, because this rotating magnetic field is what's going to wind up generating the torque on the rotor that's causing it to spin. Okay. So we're first going to consider a three-phase stator. So I'm not going to even bother putting a rotor in this system at all as of yet. So here is my poorly drawn stator. And up here in the 12 o'clock position, I'm going to put label A. And then down here in the 6 o'clock position, I'm going to put A prime. Okay. So effectively, this is the send and return path of one of our three-phase currents. Okay. So consider A to kind of be like the positive polarity and A prime to be the negative polarity of that winding. So one of them is going to be carrying current into the page. The other one has to be carrying current out of the page because they form a closed loop system. Okay. 120 degrees out of phase with our A winding, we are going to have our B winding. So I'm going to put B over here, and then B prime over here. And the colors that I'm using, black, blue, and red, are the common colors associated with the A, B, and C phase of a three-phase low voltage system. Okay. So 120 degrees out of phase with the B windings, we'll have the C windings. And then over here is our C prime winding. So this is basically what a three-phase, two-pole stator winding looks like. So our three windings are going to carry sinusoidally varying currents. So let's say that our current in the A winding is just going to be Im cosine omega st, and plotted as a function of time, we're going to have something like this. So it's going to start up here at Im that's slightly smaller. So there's Im, or excuse me, Ia in black. IB will be in blue. So it'll be Im cosine omega st minus 120 degrees. So it's going to start down here, and it's going to hit its peak, put it right about here. Something like this. And then IC will be Im cosine omega st minus 240 degrees. Something like this. And I'm going to put some dashed lines here for different times that we're going to look at things, right? So here at the origin is going to be T naught. Then right here, this is going to correspond to a time T1. Right here will correspond to a time T2. Right here will correspond to a time T3. And then right here is T4, which is effectively the exact same thing we had at T naught. So we're really going to be looking at four different points in time. So the first point in time that we're looking at is when our A phase current is at its maximum. Then the next point in time is when our A phase current is 0 and decreasing. Then when our A phase current is at its minimum. Then when our A phase current is at 0 and increasing, and so on and so forth. Okay. And so what we're going to be looking at is what our net magnetic field is going to look like. Okay. So we're just going to take a snapshot of what the currents are doing effectively at these different points in time. So at T is equal to T naught, our currents will have the following values. So we'll have IA at T naught, it will just be at its maximum, okay? And then IB at T naught will look like negative 1/2 of IM, and IC at T naught is also negative 1/2 of IM. So if I were to draw our magnetic field, let me do a quick and dirty picture of a stator here. Probably make a copy of this to make this a little easier from here on out. So A prime, B prime, C, and C prime. So since IA is positive, this current's going to be flowing out of the board. This current's going to be flowing into the board. And so the magnetic field generated by this winding is going to be in this direction. Okay, so this is the magnetic field generated by the A phase. Okay, so the right-hand rule tells us that if we have current flowing kind of in a loop where it's coming out of the board and circling back into the board, we should have a B field that's directed to the right, like so. If we look at our B phase, the positive polarity terminal of the B phase, which actually I got them mixed up. Sorry about that. So this should be B and B prime. So the positive polarity terminal of the B phase is carrying a current of negative IM2, which means we should see the tail end. And then the positive end should be coming out of the prime. And so that's going to generate a magnetic field in this direction. And it's going to be slightly smaller because the magnitude of the current isn't as big, right? So this is B sub B. And then looking at our C phase, we are going to have positive polarity here, negative polarity here. Because the current's negative, this is going to look like the tail end. This is going to look like the positive end. And so we'll have a current of the same magnitude as the B phase, but in a different direction. This angle is going to be exactly 60 degrees. And so what should our net magnetic field direction be here? It'll be in the direction of BA. So all of it will be directed to the right because whatever vertical component we have from BC gets canceled out by the vertical component from BB. But we have horizontal components that are just going to add together all in the direction of BA. Exactly right. So our net field is going to be whatever the maximum value is for the A phase plus 1/2 times cosine of 60 degrees plus 1/2 B max times cosine of minus 60 degrees. And this comes out to be 3/2 of whatever the maximum value of the field is. And I'm going to put this arrow so that we have direction to the right. So we have this field strength with this direction. Copying this picture to make my life easier. All right, so now let's look at what's going on at T is equal to T1. So at T is equal to T1, if we look here, we can see that our A phase current is 0. And our B and C phase currents are going to be not 0. So the B phase current looks like it's positive. The C phase current looks like it's negative, and we'll just use a little bit of trig to figure out what those values are going to be. So we'll have IA at T1 is equal to 0. Sorry, let's do IB in blue. So that's going to have a value of square root of 3 divided by 2 times IM. And IC at T1 will have negative square root of 3 divided by 2 times IM. So if I put my rotor picture on here, or excuse me, stator picture on here, delete the stuff I don't need for right now. All right. So since the current in the A phase is 0, I'm going to leave both of those circles blank. There's no current, so there's no current flowing in, nor is there any current flowing out. For the B phase, our current is positive. So that means there's current flowing out of the board here and into the board here, which means we should have a magnetic field that's in this direction. For our C phase, we are going to have a negative current. So that means the positive polarity has current flowing in, the negative polarity has current flowing out. And using our right-hand rule, here is our current BC. So same magnitudes, but they're askew from each other. There is 30 degrees on this side and 30 degrees on this side, oriented with respect to that vertical. So what's our net field direction going to be? Straight up, absolutely right. Okay. And so the magnitude of that net field is 0 plus √3/2 times B max cosine positive 30 degrees plus square root of 3/2 B max times the cosine of negative 30 degrees, which comes out to be exactly 3/2 of B max with the direction up. So our field strength has stayed constant, but we're now 90 degrees away from where we started from. Now let's look at what's going on at T is equal to T2. So we look up here at T2, now our current IA is at its negative peak, so it's going to be negative IM, and it looks like the B phase and the C phase are equal to each other, and they're both positive. So that's going to give us IA as a function of time is negative IM. IB is going to be positive IM over 2. IC is also positive IM over 2. And so this is going to look effectively exactly like what we had for T at equal to T naught, except that all of our directions are going to be reversed because our currents have the exact same magnitudes as they had then, but they're all in different directions. Right? So we should have a dot here, that should be black, sorry. An X here, generating a field in this direction. We should have, let's do C next, excuse me, B next. We should have a dot here and X here. And so that means we have current, excuse me, field in this direction. And then we need a dot here and an X here for a field in this direction. And hopefully it should be very obvious, since literally we have the exact same situation as we had before. I'm not going to bother with the math part. Our net magnetic field is 3/2 whatever the maximum value is, directed to the left. And then finally, at t is equal to T3, we look back up here. It's effectively the exact same situation that we had at t is equal to T1, except that all of the directions of our current are reversed as well, right? So IA is 0. IB is negative √3/2 times IM. IC is negative √3/2 times IM. And our net magnetic field is going to be 3/2 B max, but it'll be direction down this time because it was direction up at t is equal to T1. So we have a magnetic field that had some fixed magnitude directed to the right at t is equal to 0, then 90 degrees up at t is equal to T1, then to the left, then down, and it's just going to do that over and over and over again. So our magnetic field is going to have a constant strength in the air gap, but it's going to be rotating, and it's going to be rotating at whatever speed we excite our stator at, right? So we have a rotating magnetic field with a constant value that's rotating at the excitation speed of our stator. So that's how we get our rotating magnetic field. Now, let's take that and talk about the generation of torque on the rotor. So I'm going to draw a very simplistic cross-section of a squirrel cage rotor. Where this bit right here is an end ring that's holding the structure together. And then we're going to have two conducting bars that are 180 degrees out of phase with each other, right? So this is a conducting bar. And this is a conducting bar. And deep into the board, there's another end ring so that we have a closed loop, okay? So we have a ring, two bars, and then another ring so that current can circulate around that closed path. So interior to this rotor, we have our stator's magnetic field that is rotating counterclockwise at some speed omega s. And I just chose to start with it oriented up, but it's spinning counterclockwise at whatever speed our stator field is excited, or our stator winding is excited at, okay? So because we have a changing magnetic field, and right now let's assume that these conducting bars are held still here, because our magnetic field is rotating, our conducting bars, or that loop that's formed with our conducting bars, is seeing a changing amount of magnetic flux, right? Because when the field is oriented this way, effectively there's no flux that's passing through our loop formed by the rotor. When we're at 90 degrees, we have our maximum amount of flux that's passing through the loop in a particular direction. When we're at 270 degrees, then we're at the maximum amount, but it's in the opposite direction. So we have a maximum value of our flux and then a minimum value of our flux. So if we have our stator magnetic field rotating, we are going to see a sinusoidally varying magnetic flux in our loop, which is going to cause a voltage to be induced, because anytime we have a changing magnetic flux, we induce a voltage. And because we have a closed system, that voltage is going to cause a current to flow around our rotor as well, okay? So our induced voltage will be E induced is equal to V rel crossed into our stator magnetic field, and this is dotted into some length, okay? So this quantity V rel is the relative velocity between the stator field BS and the rotor, and this length L is literally just the length of one of the conducting bars. So we have an induced voltage and therefore an induced current in this system because we have a closed loop configuration. And Lenz's law tells us that the induced current is going to flow in the direction that generates a B field that's trying to keep the flux of the loop constant, okay? So now let's consider this to be kind of a snapshot of what's going on, right? So let's say that one of our conducting bars is carrying a current into the board. So this current I is flowing into the board, and then I'm going to multiply it by this length L, because what I'm going to apply is what's called the Lorentz force law. And the Lorentz force law says that our force, F, is equal to I in the direction that it's traveling, so L, crossed into B. So our B field is oriented up like so. So what should the direction of our force be, right? So in order to do a cross product like this, we can use the right-hand rule. So my index finger is the direction of the first term in my equation, right? So my index finger is pointed out of the board. My middle finger is going to be pointed in the direction of the field, which is up. So my thumb is pointed in the direction the force is being applied, which is to the left. So I have a force that's being applied to the left, like so. So I'm going to put that over here, right? So if I have change color, current flowing in this direction for this conducting bar, I'm going to generate a force oriented to the left. What about what's going on down here, right? So if current is flowing out of the board for the conducting bar on top, it has to be flowing into the board on the conducting bar on the bottom because they form a closed loop, right? So here's my I times L. My B field is still in the up direction because we're just looking at a snapshot of this thing. I don't know, there we go, why this has stopped writing. What should the direction of my force be for this case? To the right, exactly right. So our current is flowing into the board. Our field is in the up direction, and so my thumb is pointing to the right. So our force is acting in this direction. So I'm going to put that over here. So what happens if I have a ring that's mounted on a pivot and I pull in one direction on the top and pull in the opposite direction on the bottom? It's going to spin, exactly right. So this is how we've developed torque on our rotor. Okay. What is the limit on how fast it can spin? What's that? How much force that we apply? So to some extent, but so let's talk our way through this. So the amount of force that we put on this thing is going to have some impact on the speed of rotation and all of that kind of stuff. But if we look back up here, the induced voltage, E induced, is equal to the cross product of the relative velocity crossed into the stator field, where the relative velocity is the difference between how quickly the stator field is moving and how quickly the rotor is moving. If they move at the same speed, what's the relative velocity? 0. So if they're moving at the same speed, what's the value of the induced voltage and current? 0. What's the value of the force if they're moving at the same speed? 0. So they can't move at the same speed because if they did, the rotor wouldn't actually turn. Okay? So this is going to bring up the concept of slip. Effectively, we're going to see that our rotor always spins at a slightly slower speed than our stator field is moving, because if we don't have that condition, we don't have an induced field and our induction motor doesn't have anything to do. Okay? So let's write this down, okay? So since the rotor is spinning because its conductors are trying to maintain a constant magnetic flux, the rotor can never turn faster than the speed of the stator field. So our stator speed, NS, is 120 pi times the frequency at which our stator is excited, divided by P, the number of poles. right? This is the exact equation from the PowerPoint earlier, okay? So the rotor only turns if it is carrying an induced current so if N sub M, the mechanical or rotor speed equals N sub S, then V relative is equal to 0 and E induced will be equal, I induced will be equal to 0. So from this, the mechanical rotor speed, Nm, is always less than Ns. All right, how are we feeling about how things are working thus far? Trying to make it make physical sense to you guys, because that's how I figured out how all this works. I had to go through and bit by bit figure out what was going on. Okay. All right, so let's talk about slip and slip speed. So the slip speed of an induction motor is N slip is equal to Ns minus Nm. The slip speed is literally just the difference between the speed at which our stator field moves and the speed at which our rotor is physically moving, okay? Slip defines the relative motion of the rotor with respect to the stator. So our slip S will be defined as the slip speed Ns minus Nm divided by Ns, and this will be the same as the angular frequency of the stator current minus the angular frequency at which the rotor is spinning divided by the angular frequency of the stator current. So we can manipulate this expression to find that Ns minus Nm is equal to the slip times Ns, and therefore our mechanical speed is just our Ns, our synchronous speed, our stator field speed, whatever you want to call it, minus SNS, or Ns times 1 minus slip. So using these relationships, we can infer the following pieces of information, okay? Number one, if the slip is equal to 0, then our rotor is spinning at the same speed as our stator. If our slip is equal to 1, then our rotor isn't moving at all. If our slip is between 0 and 1, then the rotor turns at a speed between 0 and ns. So this is normal operation. If our slip is greater than 1, that means that nm is less than 0. What do you guys think that means? Our mechanical speed is less than 0. Exactly right. It's moving in the wrong direction. So if our stator field is moving counterclockwise, and that means that our mechanical speed would have to be clockwise. What could cause something like that to happen? We would have to apply some sort of external force on our rotor to make that happen. So effectively, we are physically breaking, braking the system. We are causing the rotor to slow down effectively by doing that. So this can only happen if mechanical power is provided to force the rotor to spin opposite the stator field. The rotor will develop a braking torque forces the motor to stop. And then our last case is if the slip is less than 0. So negative slip, okay? So if our slip is less than 0, then Nm, our mechanical rotor speed, is greater than Ns, the speed of our stator field. So effectively, we are putting mechanical power in to cause our rotor to spin faster than our stator field. And so our induction motor is behaving like a generator. We are putting mechanical power in to get electrical power out. All right. So now let's figure out what the electrical frequency of the rotor is, right? So we, at this point, have some grasp on how quickly the rotor is physically spinning, but how quickly is the current flowing in the stator windings, or excuse me, in the rotor windings changing? That's what we're figuring out here. So when the rotor of an induction motor is spinning, the frequency of the induced currents and voltages in the rotor will have a different frequency than the stator field. They have to because they're not spinning at the same speed, right? So this is because of the relative velocity between the stator field and the rotor. So while running, the frequency of the induced voltages and currents can be expressed as FR, so this is the frequency of our rotor, and this is an electrical frequency, is the number of poles times the slip speed divided by 120. Now, since our slip speed is equal to S times NS, we can rewrite our equation as simply S times P times NS over 120, or just the slip times the frequency of our stator excitation. So this is actually kind of interesting here. Like, it seems relatively intuitive, but if we think about things, so let's say that our frequency of excitation for our stator field, just as a quick thing here, let's say that Fs is 60 hertz and our slip is 2%. What would our frequency of our induced, I don't know why this went right. Okay, that one must just be run out of batteries. What should the frequency of our induced voltage and currents be? Yeah, so like 1.2 hertz, really, really honking slow, right? Like, to me, at least intuitively, I understand that the frequency of this rotor quantity should be less than the stator quantities because the motor is spinning slower than the stator is moving. But it seems odd to me, like, because the rotor spins at a frequency that is just, or a speed that is just a little bit less than the stator field is moving, I would expect the induced voltage and currents to have an excitation frequency that is just a little bit less than the stator, but it's the other way around. So if the speed at which the rotor rotates is almost the same as the speed of the stator field, then the frequency of the induced voltages and currents will be almost zero, right? So it just works a little bit backwards to the way that at least I think about it in my head. So I wanted to point it out because I find it to be interesting, right? So 0.02 times 60 hertz should be, I think, 1.2 hertz. All right, so let's wrap things up for the day because I know I've talked for 85 minutes straight at this point and you all are yawning. It's okay. Let's work one example and then we'll be done for the day. It is rather warm in here, but it's okay that my robot voice bores you as well. So let's say that we have a 50 horsepower, 60 hertz, Y connected induction motor. And it operates at a shaft or rotor speed of almost 900 RPM. When unloaded, and a speed of 873 RPM fully loaded. I want us to determine the number of poles for the motor, P, the slip frequency of the motor. So this is the same thing as the rotor's excitation frequency. So FR. And I also want us to find the torque of the motor at full load. All right. So for part A, we have the relationship that NS is equal to 120 pi times the excitation frequency of the stator divided by the number of, right? I'm sorry, what was that? Oh, it's, sorry, not 120 pi, just 120. 120 times our stator excitation frequency. So from the problem statement, which of these pieces of information do we presently have? So FS is 60 hertz. Let's write that down over here in blue, okay? So FS is 60 hertz. I agree with that wholeheartedly. All right, we're told what the rated power for our motor is. We're told what its frequency of operation is, which is by definition going to be the stator frequency because that's where we're applying the power to it. So that's where that 60 hertz comes from. All right. So 120 is just a constant, so that's easy. We're trying to find P, the number of poles. So it seems to me like we need NS. Is that something that we were given? What is it, Bailey? 900, exactly right. So the speed that our motor is approaching at unloaded conditions is effectively going to be our stator speed. So that almost 900 RPM tells us that NS is 900 RPM. So we do the math here. Our number of poles, P, is going to be 120 pi times Fs over NS. And so that's going to look like 120 pi times 60 divided by 900 gives us 8 poles. Now, I want to point out here that I intentionally did not use any units because this equation is one of the very few equations that literally should not have units in it anyway. So that 120 effectively has implied units that are going to work out how to give us the number of poles here. So it's going to wind up having some weird conversion between revolutions per minute and revolutions per second and all that kind of stuff. It's built into there. So literally just don't worry about the units with this equation. It'll be way easier than trying to figure out what the hell the units need to be on that 120. Okay. So no need for units whatsoever with this particular relationship. All right, so we have an 8-pole motor. How do we figure out our slip? I think we should just use the equation for slip, right? So our slip, or actually we're looking for our slip frequency, right? So FR is equal to S times our stator frequency. We know our stator frequency, so now we need to figure out what our slip is. Slip is NS minus NM divided by NS, and we have all of those pieces of information, right? So that's going to be 900 RPM minus 873 RPM divided by 900 RPM, and that comes out to be 0.03 or 3% slip. So from that, our slip frequency of the motor is 0.03 times 60 hertz. Is 1.8 hertz. The last thing that we're asked for is the torque. So I'm trying to decide whether or not I want to derive a relationship for the torque using physics relationships, or if I want to direct you back to something that I mentioned really in passing at the very beginning of our last class meeting. So if we go back way to the front page of this thing, first thing that I talked about was that our output power, P out, was equal to torque times angular frequency. We have an output power, 50 horsepower. We have an angular frequency. So it seems to me like we should be able to figure out torque from those two numbers without going through a whole bunch of weird conversion things. Right? And by the way, the whole bunch of weird conversion things wind up giving us that exact relationship. So we can say that our developed torque is our output power divided by our mechanical rotation speed, omega m. Okay. So our output power is 50 horsepower, and our rotation speed is 873 revolutions per minute. What should our units of torque be? You guys had physics classes and all that kind of stuff, right? So newtons is force, not newtons per meter, newtons times meter, right? Because torque is force applied over a distance. So force times distance. Newtons times meters is the unit of torque, okay? And that is effectively a newton times a meter is also a joule, okay? So how are we going to get this to look like joules or newtons times meters? Anybody got any thoughts there? So, okay, so convert horsepower to watts. Fantastic. How do we do that? 746. Close, but 746, okay? So 746 and some change, but let's leave it as 746 watts per horsepower. All right. So horsepowers cancel each other out. Now we have watts, and we're trying to get, let's see, so something in joules would be watts times seconds. So right now we have watts times minutes effectively. So how are we going to sort that out? Okay. So there is, in every 1 minute, there are 60 seconds. Okay. And now we're left with a revolution. So effectively what we're doing here is we're converting our angular frequency omega m into a linear frequency that's just measured in cycles per second or revolutions per second. And so that conversion factor is literally, there are 2 pi radians, which is a dimensionless quantity for every revolution. Okay. So revolutions cancel, minutes cancel, and we're going to wind up with watts times seconds, which is the same thing as a joule or the same thing as a Newton meter. And this comes out to be 408 Newton meters. So I just wanted to lead you through the unit conversion that we're going to be using to figure out what our torques are. A Newton meter is the same thing as a joule, which is the same thing as a watt times a second, right? Because we have watts divided by 1/seconds, that's the same things as watts multiplied by seconds, which is inherently a unit of energy. Yep. All right, that's enough ranting out of me for the day. You guys have a great rest of your afternoon, and I'll see you on Thursday because I believe today is Tuesday.